Welcome to this webinar about 5G and R millimeter wave and the challenges that come along with it, especially for device testing. First of all, let's have a look on the different frequency ranges that are specified for 5G and R. And as you probably know, there is basically two different frequency ranges. That's frequency range 1 with up to 6 gigahertz. And then there is frequency range 2, which is the millimeter wave frequency range going from 24.25 gigahertz up to 52.6 gigahertz in release 15. As you probably also have heard, in December last year, there was a RAN meeting where they decided on an extension of the frequency range 1 to extend it from 6 gigahertz up to 7.125 gigahertz. Now, in frequency range 1, as was also mentioned in the abstract for this webinar, I would actually try to summarize it in a way that I say frequency range 1 5G and R is kind of the logical evolution of LTE, but of course with more flexibility, with more features, with more possibilities, and especially with higher data rate means more bandwidth. So let's have a quick look into FR1 and in 5G and R general topics before we then move into the millimeter wave range. If you look into FR1 specification, there is more than 30 bands specified for sub-6, or maybe I should better say sub-8 now. So basically in the frequency range 1. And you see all these bands listed here. We don't need to go through all of them in detail, but generally speaking, we have, similar to what we had, for example, also in LTE, of course, a lot of bands for FDD. We have a lot of bands for TDD as well. And the interesting part of this table is actually, if you look at this bandwidth column here, the majority of these bands are fairly small, actually. They are like below 70 gigahertz. And a lot of those bands are actually also reused from what was specified in LTE. But then on the other hand, we have a few really interesting bands in FR1. They are the ones I listed here in bold because they are the ones that have really nice and high bandwidth. And that's what we want to achieve. For enhanced mobile broadband services in 5G and R, we want to have high data rate, much more than we had in LTE. And that again means we need more bandwidth. So you see here, for example, band 40 and band 41, they are 100 and almost 200 megahertz wide. And then further down the line, in the band 77, 8, and 9, you have these 3.5 and 4.5 gigahertz bands, which are extremely interesting for a lot of operators for running 5G and R in FR1, because they are really wide band, between 500 and 900 megahertz of bandwidth. That is, of course, way more capacity than we have in, say, LTE or other previous generation networks. And then, of course, you see here also that supplemental downlink is specified in sub-6 as well, or in FR1, which is, of course, mainly used for downlink carrier aggregation, where you don't need an uplink necessarily in the same additional band. And you have supplemental uplink. Now, supplemental uplink is not necessarily an additional uplink carrier to provide higher data rate. It is also used or meant to be used as an additional uplink if you want to have a more robust uplink connection in a FR2 link. So you have an FR2 link, which is millimeter wave, which is, of course, way more difficult to maintain. And say, to be on the safe side, you could accompany this with an additional uplink, which is in FR1. So those are those bands here, 80 and higher. Now, if we look into 5G definitions in general, then of course it's an OFDM signal. So this is the same like what we used in LTE. Therefore, we have a resource grid. And you see here on the left side as a comparison, the resource grid for LTE. So this is this one here. And then on the right side, you see the resource grid for 5G and R. Now, first of all, as I said, it's OFDM. So we have the OFDM symbols here along the time axis. And then we have along the frequency axis the different subcarriers. So here, the frequency axis, and here the time axis, the symbols. So what is different is that in LTE, we had a resource element, which is defined as one symbol, one subcarrier. That is, first of all, not different. That is the same in 5G. So here, a resource element, or over here. And now in LTE, we specify the resource block as 12 subcarriers. So this is this 180 kilohertz of bandwidth over 7 symbols. And in 5G now, we do the same in respect to the number of subcarriers, 12 subcarriers, but we do not have a fixed time dimension. And the reason for this is explained on the next slide, but this is quite a significant change because it will open up a lot of more flexibility for 5G in R. So here's the reason. In LTE, we had a fixed subcarrier spacing of 15 kilohertz. And in 5G and R, we have now flexibility. So we can place orthogonal subcarriers in 15 kilohertz or 30 kilohertz or 60 kilohertz distance to each other for FR1. And if it comes to FR2, we even have 120 kilohertz as a possible subcarrier spacing, and 240 kilohertz for control signals, only not for data. That's why I put it in brackets here. So you see now, of course, in this chart here, if you have the 7 symbols and you use 15 kilohertz subcarrier spacing, you of course have a different time domain, so to say, than if you use a higher subcarrier spacing. So the green thing here is 30 kilohertz or then 60 kilohertz, and of course for millimeter wave, then that continues in that way. So you can deliver the same amount of data over a shorter time period. So that, of course, is very interesting for time-critical communications, like is used, for example, in ultra-reliable low-latency communication. That ends in a numerology that is way more flexible in 5G than it was in LTE. Again, on the left-hand side, you see LTE, so the 7 symbols per slot, 2 slots per subframe, and then here the 180 kilohertz over the 12 subcarriers with 15 kilohertz subcarrier spacing. This is how we scheduled the data in LTE. And in 5G and R, due to now this flexibility in the numerology, the different subcarrier spacing, and also then, of course, the dynamic timing, you see here on the right-hand side what this means now in this resource grid, so to say. So we have a lot of more dynamic in the system that allows, of course, for much more possibilities to map different services together or to change between different requirements very easily. So that's, of course, way more flexible than in LTE. Then for the data rate and for the bandwidth, of course, again here, and you saw that before, we have higher bandwidth channels specified or higher bandwidth bands specified. Again, as comparison, LTE was specified for those 6 different bandwidths, up to 20 megahertz as a maximum. And you all know Shannon's law. The bandwidth is, of course, very, very important for the capacity of the radio channel. Basically means it drives the data rate. So if you want to go to higher data rate, in LTE we used carrier aggregation. We were just adding up multiple ideally 20 megahertz wide channels. In 5G we have a different possibility because we can simply go to wider bandwidth if we have the right band, of course, that we use, so a band that also supports this high bandwidth. And you see here now we have a lot of more possibilities in using different bandwidths in 5G and R FR1 that ranges from 5 megahertz wide carriers up to 100 megahertz wide carriers. And in FR2, you can even go up to 400 megahertz wide. Now, of course, not every subcarrier spacing is also specified for every bandwidth. So you see here on the side, 15 kilohertz subcarrier spacing 30 and 60 for FR1, and then 60 and 120 for FR2 data. And you can see now, of course, for example here, 15 kilohertz subcarrier spacing is not specified for this higher bandwidth. if you really want to go to 100 megahertz wide carriers, you basically automatically go to also a higher subcarrier spacing that it was used in LTE. Another nice thing you can see on this table is, if we make a comparison again to LTE, then, for example here, 20 megahertz bandwidth, 15 kilohertz subcarrier spacing. This is the LTE case. And in LTE, we had the possibility to have 100 resource blocks that we could schedule to different users. In 5G, now we have 106 resource blocks. So that means it's an occupied bandwidth of 19.08 megahertz. And that again means we have a smaller guard band between the bands in 5G than we had it in LTE. So it's a little more efficient, so to say, to run LTE even though you only have 20 megahertz, sorry, to run 5G even though you have 20 megahertz bandwidth only. And the same, of course, applies then to FR2, but just there we don't have a comparison, of course. Now, these different bandwidths and these different subcarrier spacings belong together, but of course, not every bandwidth is usable in every band, simply because you don't have the bandwidth in every band. As I said before, quite a few of those bands go up to 70 or 60 megahertz bandwidth only. So you see only, for example, in bands like band 41, which is a TDD band, which is one band with this almost 200 megahertz bandwidth. Then, of course, here you can also use 100 megahertz wide channels. That is, of course, naturally giving the definition of the different bands. And that is also true for FR2. In FR2, you can go up to 400 megahertz, as I said. That applies to all the bands, but 60 kilohertz subcarrier spacing only is possible up to 200 megahertz wide carriers. So if you want to go to this really, really high bandwidth carriers with 400 megahertz, that automatically means 120 kilohertz subcarrier spacing. Which leads us over to frequency range 2. And as I also outlined in the introduction of this webinar, here is where the complexity comes in. Because all the stuff I was talking about just up to now is general 5G improvements. They apply to both frequency bands. But the complexity and the challenges that I want to focus on now are actually coming in with FR2. And why is this? So if you look into FR2 specifications and definitions, you have at the moment 4 bands specified. These are typically in the 25 gigahertz range. So you see here 24.25 up to 27.5. Then you have this 26.5 to 29.5, typically denoted at 28 gigahertz. And then you have 39 gigahertz, which is this band N260, which is 37 to 40 gigahertz. What you can see here right away is that these bands really support a really high bandwidth, 3 gigahertz worth of bandwidth. So that means, of course, a lot of capacity and a lot of data. Of course, not one operator will have the entire band, but even if you have only a fraction of it, it gives you a lot of headroom for driving the data to really new dimensions. And this is actually the reason why everybody is pushing into this millimeter wave spectrum now. As you can also see here, there is no FDD, so it's all TDD because of the reciprocity of the channel. And of course, in TDD, we have an advantage if we go to beamforming, and that is required in those millimeter wave bands, as you will see further down the line in my presentation. So, first of all, why do we do millimeter wave at all? I basically mentioned it on the previous slide. It's all about the bandwidth, it's all about the data rate. And if you want to drive data rate, you need high bandwidth, and if you want to have high bandwidth, you basically have to do either a lot of carrier aggregation like we did in LTE, which adds also a lot of overhead, of course, into the system, or you go to high bandwidth, the higher the better. And that's why we, in 5G, go into these high frequencies, because this is where we can find the high bandwidth. Now, high frequencies, high bandwidth, that is nice. What is the downside, though? The downside is that the path loss goes up. So the path loss in millimeter wave bands is of course much higher, because you see here the formula for free space path loss, and here you have a frequency dependency, of course. So that means that if we go now from, say, 1 to 3 gigahertz FR1 frequencies to 28, 39, or even up to 52 gigahertz bandwidth in FR2, we have 30 dB more free space path loss in the system. So I have here two examples. On the left side, you see typical ranges of chambers when you would do lab testing. They go from between, I don't know, 2 meters to 5 meter chambers maybe. And just an example here for a 3 meter chamber, you would have in a typical FR1 frequency range of 1 to 3 gigahertz, something like 45 dB free space path loss. If you do the exact same thing, but just on a higher frequency between 30 and 40 or 50 gigahertz, you end up with 75 dB path loss, so 30 dB more. The same, of course, applies, like you see on the right-hand side, as well in small cells. So in the field, if you have like a 200 meter range, you drive the path loss from 80 to 110 dB. And that, of course, is critical, because it means a lot of more sensitivity requirements on the receiver. It needs a lot of more output power requirements if you wanted to overcome this additional 30 dB path loss. So we have to be more clever than that. We can't just say, oh yeah, okay, we make this receiver really sensitive and we just output a lot of power and then we have 30 dB more. So what is the clever way of doing it? And of course, it's very simple. You put directivity into the communication path. So this is like if you would go and want to talk to somebody that is like at a certain distance from you and he can't hear you. So what you do is you put directivity into your talk by putting maybe your hands around your mouth to not lose too much energy to the sides, but focus your energy to the person sitting in the corner. And the exact same thing we do here, just of course we can't use hands. We have to use beamforming. Beamforming is done by active antenna systems. Active antenna systems are antennas consisting of multiple antenna elements. And each of these elements has phase shifters, amplifiers. And by changing the phase relations between the different antennas and the amplification, I can, with this, steer the energy that antenna is emitting into a certain direction. So that means we are going to radio patterns or antenna patterns in cellular phones or other terminals in 5G that look like here on this screen. So you have a main lobe, which is the majority of the energy is going to, and then of course you have side lobes, because you can just steer everything in one direction because of the antenna elements also creating side lobes, but you try to, of course, have as little energy going elsewhere and focus the majority of energy into the main lobe. Now, of course, this has implications besides on the complexity of the design, also on the way how we can test this. Because at the end of the day, it's all about no cables in millimeter wave. Why this? Because if you have a phased array like this, you have a lot of antennas. So that would first of all mean a lot of antenna connectors if you wanted to connect to this antenna at all. Okay, that's maybe still possible, also cumbersome. But there is another reason not to do that, and that is that if you would connect now a cable to this antenna, it would actually influence the characteristics of the antenna, because you go into the with a metal object very close to the antenna or at the antenna, and that changes the pattern of this antenna. And you can see here two examples. On the left-hand side, you see an antenna measured with like over the air, no cables. And then the same antenna was connected to a cable, but still measured then over the air with the antenna pattern. And you see that there is quite a big difference in the performance of the antenna just because you connect a cable. So if you would now want to do parametric measurements on this antenna with a cable, you are destroying actually the results just by measuring, because you're changing the performance and the pattern of the antenna. So this is not a good idea. And then there is another reason, and this is, of course, that the antenna itself, or the active antenna system, becomes now a fundamental part of the overall system. So you can't just shortcut it with a cable, because you're taking out this whole functionality of beamforming, and that is critical. So actually, this is what you want to test. So why would you take it out? That is not possible. It doesn't make much sense. So therefore, all the tests that we have to do in mmWave have to be done, including the antenna system, and that means they have to be done over the air. Okay, so that means we do what we did before, we just cut the cord. Well, unfortunately, it's not as simple as that. So we have to have a closer look onto this. First of all, also 3GPP, of course, realized that and specified it in this way, that everything you want to test below 6 gigahertz is tested as we did in the past for 2G, 3G, or LTE. We do it in a conducted way. There is, of course, exceptions from the rule, like antenna performance tests that we also did in the past over the air. Of course, we still do over the air. But in mmWave, everything above 24 gigahertz has to be tested over the air, and it means everything. So if you want to do an EVM measurement, if you want to do a power measurement, if you want to do a spectrum measurement, regardless, you have to do it over the air. This is specified in 3GPP. 24 gigahertz is the borderline. The lowest specified frequency for frequency range 2 as of release 15 is 24.25 gigahertz. So we are above this borderline. That basically means FR2 is OTA. So testing over the air, as I said, as such is nothing new. It was done before, but below 6 gigahertz and only in certain cases like antenna performance tests. But now with FR2, everything has to be tested over the air, and everything has to be tested, of course, at mmWave frequencies. So therefore, of course, besides cutting the cords, there's quite a few things that we have to consider and keep in mind. For example, we now worry about the radiation pattern of the antenna, the field properties, how does the field transmit or transform over the air. We have to talk about near field or far field. We have to think about things like quiet zones. How big of a chamber do we need at all? Do we need a positioner for doing our tests? Under which circumstances? So a lot of new considerations come into the play that we simply didn't have as long as we had a cable. So therefore, a little bit of electromagnetic field fundamentals here. And for some of you, I hope this is already known, but I still want to repeat it. So if we have an antenna, and basically my antenna sits right here on the left side here in the center. This is the antenna, and it's emitting waves. And you see here also a certain directivity, so it's kind of a beam forming. So this would be the main lobe, and then you see here some side lobes as well. But the important thing here, this antenna is emitting in this direction. And we can distinguish basically the field that is created into 3 different areas. The first thing here is the so-called reactive near field region. The reactive near field region is a region you don't want to be in, because if you would go in here to do parametric tests with another receive antenna, or maybe even with a cable, that was my example from the slides before, you would automatically change the behavior of the antenna. So everything that is in here couples to the antenna and becomes part of the radiating element, and it changes the behavior. So stay out of the reactive near field unless you do things like SAR measurements, for example. So for parametric measurements, you don't want to be there. Then we have over here, this is actually where it's really nice and easy. That's the far field. This is where we ideally would be, because here everything is easy to measure and it's just nice. In far field, I will explain later on, we have great conditions for our testing. Or then in between, we have the so-called radiated near field. Radiated near field is also possible to test, but things are just a little more complicated, because in radiated near field, we have different properties of the field components, and therefore the measurements that have to be done include magnitude and phase measurements, typically around the entire sphere of the antenna, and therefore they just take a long time. So ideally we would be in far field, as I said, but now where is the far field? There is a formula that is down here, 2d squared over lambda. Lambda is the wavelength, so say we are at 28 gigahertz, and d is the aperture size, so the size of the radiating element, the antenna, and say that would be 10 centimeters, 0.1 meter. Then, under these conditions, far field is at, say 1 meter 90, 1 meter 87 to be precise along this formula. Reactive near field is at 19 centimeters, so you should stay away at least 19 centimeters from the antenna, and ideally you would measure in a distance of 1 meter 87 or beyond. That is, of course, a little difficult because that means big chambers, a lot of space requirements, but however it's necessary. And the reason is that in far field you have the E and H components, so the electrical field and the magnetic field components of the electromagnetic radiation from the antenna being orthogonal to each other. Therefore, you don't need to worry about the phase because the phase is known. The resulting so-called pointing vector is shown here. So it's again orthogonal to the other two components. And you know, we all learned this in physics sometimes back in school. This three-hand rule, or this right-hand rule, sorry. And so as soon as we are in the far field, we only have to measure the radial component of the pointing vector, and that means it's just a power measurement, basically. So it's simple. We don't need to worry about phase. This is different when we are closer to the antenna. And now, where is this? Where does the far field start? As I said before, there is this 2d squared over lambda formula that was defined by IEEE. Now the question is, why is it 2d squared over lambda? What does it mean and where does this come from? And I want to explain here on this slide. It's also called the so-called Fraunhofer distance. And you see here on the right-hand side actually how it is defined. So if we have nd squared over lambda, and we go from n being 1 to higher n's, so from d squared over lambda to 2, 4, or 8 d squared over lambda, then you see on the right-hand side the resulting curves. So ideally, we would have an infinite d squared over lambda. That would be the blue curve, and that would give us the real radiation pattern of the antenna. We would see the main lobe here, we would see side lobes, and we could even see the nulls. Of course, that means also that we had an infinitely big chamber. That's not possible, so we have to find some compromises. And the compromise was, at the end of the day, to go to 2d squared over lambda, which is this red curve, n being 2. And that gives us a good compromise of being able to measure, of course, main lobe, being able to measure side lobe on a pretty good accuracy, and being able to identify even the nulls in this transmission pattern. And this is how this Fraunhofer distance was defined and specified. So 22.5 degree phase deviation of the signal is still okay. I said before, actually, phase wouldn't matter because it's all orthogonal. Well, it's a compromise. It's not really, really orthogonal, but we allow 22.5 degrees phase deviation to still be good enough. And therefore, we can, of course, limit the size requirements for those chambers. And then, if we are in this far field, we have what we call a quiet zone. And the size of this quiet zone, well, is defined with these deviations. Well, 22.5 degree phase deviation within a certain area is allowed. And how big this area is basically defining the quiet zone. Of course, right at the borderline, this area will be very small. If we go a little bit further, this area will be bigger. And this defines a quiet zone. Now, of course, this is how it's defined in the specifications. The resulting quiet zone has, of course, certain other parameters as well that we need to consider. Like, for example, besides a phase deviation, also an amplitude taper. So ideally, I would have a plane wave coming towards me where if I measure the power along this plane wave, it would be always the same power level. However, that would be in an ideal world. We are only 2d squared lambda away, so the curve, the radiation is still curved a little bit. And 22.5 degree phase deviation is okay, and also the amplitude deviation, of course, has to be specified. So how much do we actually go away from a real plane wave in respect to the amplitude? That is defined by the amplitude taper. Typically, things like 1 dB taper, for example, are specified, or maybe also 2 dB taper. And of course, this is a measure to define also the size of the quiet zone and the quality of the quiet zone. Besides, as you see on the right-hand side, there is also a ripple around this received signal, a received wave. So it's not ideally plane and it's not ideally flat. So there could also be a ripple, and also this ripple, of course, basically defines the quality of the quiet zone. Ideally, you would have totally flat without any ripple, but this is not an ideal world, so we have to look into these details to specify the quality of the quiet zone. Now, what size of a quiet zone is actually needed? So how far do I have to go away to be able to measure my device under test? Do I need a huge quiet zone? Do I need a really tiny quiet zone? Well, again, this depends. Basically, it depends on d, because lambda is given, 2d squared over lambda is the border again. Lambda is given from the frequency that I'm using my device in, but how big is d? D depends now on your particular use case. So if you know, if you are in R&D, for example, and you have a device and you know exactly where the antenna is, and you know also the dimensions of the antenna, then of course this can be considered as D. You know the dimension and the position of the antenna, and it can be fairly small, maybe 2 or 3 centimeters only. I put here an example with 3 centimeters, and since you know the interior of the device, this is called white box testing. If my D is 3 centimeter and I'm working with 30 gigahertz, because 30 gigahertz is exactly 1 centimeter range length, so you can also do the math on the top of your head. So with a 3 centimeter D squared is 9, 2 times D squared is 18, divided by 1 centimeter lambda, so we end up with a far field distance of 18 centimeter. So as soon as we are 18 centimeter away from this antenna, we are in far field and everything is nice and easy. The complication comes in if you don't know where the antenna is. Then this is called black box testing. So if I look at my phone in my pocket, I don't know where the antenna is. So then I have to consider the entire size of the device, because it could be anywhere. And then of course my D becomes much bigger than 3 centimeters, for example, for a standard smartphone, maybe 12 centimeters. And that, of course, at the same frequency leads now to a far field distance of almost 3 meters. So from nice and easy 20 centimeters, we move to a 3 meter, which is like a room size far field distance. On the next slide, you see a graph that basically shows you a nice overview on how big of those rooms or chamber requirements will get with the different device sizes or the different black box and white box requirements. So again, given 12 centimeter device size, and you see here now the curves are ranging from 24 to 40 gigahertz, just as an example. And that means if I have a 12 centimeter quiet zone requirement, I end up with range lengths between 2.3 and 3.9 meters. And that, of course, means chamber sizes, because the chambers has to be a little bit bigger than the range length, of course, chamber sizes in the range of 3 to 5 meters. If I have white box testing, so my 3 centimeter example from before, then I end up somewhere down here in the range of 10 to 30 centimeters. So a small shielded box with half a meter would do the job, and I would be able to test in far field. That, of course, depends a lot on, again, your D and your frequency range. And now we are in direct far field. So we are exactly what you saw before on this radiation properties on the far right. So we didn't do anything else than just emitting the wavefronts, and we are over here in the far field, in this far right field area where everything is nice and easy. But we have to be, for example, 3 meters away. Now there is other means of shrinking that size requirement. And I want to explain this now. So it's kind of like far field testing, but in a physical dimension that matches actually near field requirements, or matches near field distances, I should better say. And with this, you basically do a transformation of the field components into the far field. You manipulate the field components. There's different ways of doing this. You see here on the left, Fresnel lenses would be one possibility. So you have a point source that is emitting waves, and then they are here going through this lens, and with this they are evened out, so you create a plane wave. That's not so commonly used. It's more like in research environments maybe, but in industrial applications you find more CATR, compact antenna test ranges. This works as a reflector, so you have again a point source emitting a wave towards the reflector is reflecting it as plane waves. And there is a third possibility how to manipulate now this field, which is given here on the right, and that is a plane wave converter. I will briefly explain those two possibilities to create far fields in a near field distance. So first of all, CATR, compact antenna test range. As I said, it's a reflector, it's a feed horn, and the feed horn is transmitting spherical waves towards the reflector. You can see this here. And the reflector is reflecting that in this direction, and this is where you place your device under test, nice plane waves. Of course, within the given limits in respect to phase and amplitude taper, ripple, all the stuff I was talking about before. So this is the theory. It looks then like this. Feed horn, spherical wave emitted from the feed horn to a reflector. The reflector size would be, say, n centimeter. And then over here, the reflection of this waves from the reflector are plane waves. And you create over here a quiet zone of half n centimeters. Number of thumb. This is really depending on the design of the reflectors and all that. But number of thumb, you can say, if you have a, say, 20 centimeter reflector, you end up in something like about 10 centimeters of quiet zone. Rohde&Schwarz, of course, has a nice product that does exactly that. It's called ATS 800B, and you see here a picture here, which is exactly what you saw before, a feed horn, a nice reflector with 42 centimeter square, and then it's projecting over here, so this is where you would put your device under test, and it's creating a 20 centimeter quiet zone. The size of this setup is approximately 0.4 by 0.8 by 1.2 meter, and it's meant for frequency range 2 R&D testing. So you can put it on your benchtop, put your device there, and you have a nice and quiet 20 centimeter quiet zone. If you tried to achieve a similarly sized quiet zone in direct far field, you would end up, just as a comparison, with 30 gigahertz frequency, you would end up in an 8 meter range length, so in a 10 meter chamber. And this is like 1.20 meters only. The nice thing about this is we also mount it upside down, so to say. So we turn it by 90 degrees. Then it's called ATS 800R, and the R means rack. So it's integratable in a rack. Same dimensions, same quiet zone, etc. applies. But of course, it doesn't take much floor space in your lab, for example, because you have probably a ton of racks standing in your lab anyways. So typical rack sizes. And you create here the same quiet zone of 20 centimeters inside this rack. And it still allows you a lot of room down below for placing directly your equipment that you want to test with when you do the performance tests of your devices, for example, your devices under test. Or alternatively, you can also put this reflector into a chamber. We have a chamber called ATS 1800C, and this creates, with a little bit bigger reflector, a 30 centimeter quiet zone in a chamber size of about 1 by 1.5 by 2 meters. Again, if you compare this quiet zone size with direct far field, you would need for 30 gigahertz 18 meter distance. So you end up in about a 20 meter chamber, where this chamber is, as I said, 1 by 1.5 by 2 meter, number of thumb. So you of course tremendously shrink the space requirements you're having. So this was for CATR. I mentioned before there is another alternative for doing far field requirements or far field conditions in a near field distance, and it is plane wave synthesis. So you see this here. It basically works like this antenna systems work. It's a multitude of antennas and they are connected via phase shifters. The reason for doing this, and this is actually coming back to FR1 now, this is actually meant for sub-6, so for FR1 testing. The reason for doing this rather than CATR is that CATRs become really, really big for big devices at low frequencies. So they become big, expensive, large and heavy, hard to handle, hard to manufacture as well. And with plane wave synthesis, it's much more compact and lightweight compared to a CATR reflector. Also, another advantage of this approach is that the distance between the reflector and the device on the test, typically in the CATR system, is about 3 to 4 times d, whereas in the plane wave synthesis, you can go down to half of the distance between the device on the test and the plane wave converter. And again, Rohde&Schwarz introduces a product that is called PWC200. And the nice thing is here, there is one RF cable going into this ring of antennas. There is 156 Vivaldi antennas in here. They are connected via phase shifters and amplifiers, as I said, or attenuators. One cable going in, so you can hook it up to your tester, to your generator, to your analyzer, to a radio tester, whatever it is. And it generates a nice big quiet zone of 1 meter at a distance between the plane wave converter and the device under test, or the antenna under test, of only 1.50 meters. If you would want to do the same thing, again, in direct far fields, for example, at 3 gigahertz, again, this is FR1, mainly meant for base station testing for big devices that need a big quiet zone, then you would again have a 20-meter distance requirement between the device under test and the antenna, or your emitting antenna. So this, of course, again, shrinks the space requirements to a huge extent, and it eases your life in your R&D work because you don't need to go to the chamber all the time. You can do this at your benchtop, maybe with the ATS-100B or the ATS-800R in the rack, or of course, with a plane wave converter if you do base station testing, still in the chamber, but in a much smaller chamber. If you want to learn more about all the stuff I was talking about, or if you want to have a nice summary for all that, we actually just created a nice OTA testing fundamentals poster. You can download this on the link given on that slide. It's talking about more or less all the stuff I was explaining throughout this webinar. And if you're interested in also seeing some of those instruments or some of these setups that I was talking about, PWC or ATS-800R, for example, or 1800C, live, and of course, many, many more nice solutions about 5G and R testing from Rohde&Schwarz, then please come and visit us in Barcelona at the Mobile World Congress. You will find us in Hall 6. I'm looking forward to seeing you there. Thank you very much.